Okay, so it's one thing to know that we've collided, but and it's important, right? So we've already seen, in various ways that we want to understand when we're colliding. We want to understand when our bullet hits our target, or when our axe hits our character, so we can know that damage has occurred. We can also look at the simpler cases. When have we hit our trigger that opens up the door, or we're standing on the right platform to cause a cascade of traps to ignite. So collision is one thing, but it's what we do with that collision that matters. And so let's kind of step back for a minute and talk about sort of basic physics and how things work, right? And so the most basic physics is sort of Newton's first law: an object in motion stays in motion, and that can be represented here. You'll see that it starts to feel and look similar to the ray and lines. So we have a position that we start with, a p init, and we have a direction that we're traveling, and this direction also includes a speed with it. And so every step of the way, every moment in time, we're moving along this direction. And so we could get very precise. We could say at 0.0001 seconds, or at 15 nanoseconds away, we can figure out exactly where we're going to be. Or even several hours from now, we can figure out we're going to be somewhere out here, right? By understanding this velocity and, again, scaling it. We don't necessarily care that this velocity needs to be unit length. It's of length speed, right? But then the direction is also encoded in there. So again, we've got vectors, we've got positions, and really what we're doing is we're taking a speed and anywhere along, or a full velocity of speed plus a direction, and anywhere along this line we can figure out what our new position is going to be very accurately, simply by multiplying time by our speed, by our initial velocity. But this is assuming that nothing else is going on, right? So again, Newton's first law, think back to taking our input key as we move forward. We're going to move along a direction and a speed, and we're going to multiply that by the delta time and figure out each step how far we're moving. So Newton's second law says that an object in motion will stay in motion unless acted on by an outside force. In this case, we're sort of treating gravity as our outside force. It's really just an acceleration. But it gets a little more complicated. We still can very accurately determine where we're going to be because the outside force is acting on us continuously. So we started with an initial velocity, but at every moment, gravity is pulling us down, and so we're going to end up following a curve that looks like this. So we'll follow a parabola, and we would continue to fall down indefinitely unless there's ground here, in which case, we know that we're going to get a collision. So again, we have a closed form, and a closed form means that we don't need to iterate through this. We can simply pick a time t anywhere at any scale, and even down to the nanoseconds again, or even several hours from now. And the math all still works out. It'll give us an answer. It'll give it, hours from now, it would give us an answer way down here, assuming that we could fall forever, which is fine. So at any point, we're picking a position and saying, this is the position that we're going to be at any point in time. And it's this equation down here, so fully predictable. Okay, but what happens if we don't know, or what can we do as we're stepping through it? So we follow what's known as finite differencing, and in the case where we have a known force which we understand and is acting continuously and predictably, then we can be closed form, as I just said. But we don't really know that, right? So we can imagine, or we can picture that our inputs are actually forces acting on our object. So we already kind of saw this with the way we set up our first-person shooter, that we press the W key and they move forward, and we stop pressing the W key and they stop moving forward. Right? This is a force that's acting or not acting from moment to moment, and we can't possibly predict when the player is going to press that button. The only thing we can do is, at any given moment, ask the player, am I going now? And this lends itself well to the way we've got video games set up. We've already got a loop where we've got a delta time, and we're moving through time along that delta time as quickly as we can. Right, so we're stepping through our loop. If we remember here, this is our update loop, and we're stepping through this as quickly as we can, but we know that there's a certain amount of time that it took us to get through here, and we keep track of that delta time, and we understand that it's going to be 0.01 if we're 100 frames per second, or 0.03 if we're 30 frames per second. And so when we're considering Euler's method, we're sort of well positioned to use it. And so the idea is that for Euler's method, rather than assuming a closed form, we're going to assume at every step we need to figure out the next step. And so we look at, say, what is our force at this time, right? So what is the input from the player, or what is the current interacting forces at this time t, and we multiply that force times delta time, right? A small step. So we said, however much time we went, 0.01. So our delta time for this step is 0.01. And we add this change in velocity. So this ends up being a change in velocity. So it's an acceleration over a brief window of time modifies our velocity. And then this represents our new velocity at the new time. And then we use our current velocity here. We multiply it times time. And we update our position in the same way. And we say our new t plus delta t, or we can even call this p of 0 and then p of 1 over here, or p of 1 and p of 2 and so on, moving through time by stepping. But we move by our small delta times each window. And so we already did this in some sense with our first-person shooter. We said move the character forward a small amount by the world delta seconds. Or we did this with our cylinders. We took the world delta seconds and we said move that cylinder along a line a very small amount, and then the next update move him again. Take the current position he's at and move him to the right or to the left a certain small amount. And so that's really what's happening with Euler's method. Now there's a slight variation called the Euler symplectic method, which actually, rather than taking the velocity of t here, it actually takes the new velocity and applies that here. And it ends up being slightly more error-proof. But the one error, or the one major problem with Euler's method, is that there is no delta t that is perfect. So where we previously knew down to nanosecond level of resolution exactly where we would land on any point on this curve, we now can't say that anymore. So by virtue of the fact that we've decided to step this red line this far, and even imagine this might be a step that represents 0.1 seconds, right? But it's still getting this small amount of error. And then from there on, we're taking this as our new position, right? So we've updated our position and said, well, this is our new position, and our new velocity is this way based on what I know about the velocity from here, and I'm going to move this way. And so we accumulate our error. We now have, a newer error that's accumulating based on the fact that we were a little wrong here, and now we're even more wrong moving through space. And so we end up adding more and more error as we go. And what this ends up looking like is added energy into the system. So it ends up being that things move a little bit faster over time, or they pick up a little bit extra acceleration that isn't really representative of the system. And we get that in part because we're using this very simple method that fits very well into our engine approach. But the counter to that is that we get an error. Now it could be that we don't care. As long as we're bounded, so we're not gaining so much energy that things are flying out of the room, or like if we're playing a pinball game, our pinball is not flying off the table, and as long as those kinds of things aren't happening, we don't care about a physically correct representation of the real world. We care about making it feel pretty good to the player, right? If it feels accurate enough, then we're okay with the result that we get, even though it might not be exactly correct. If you were to go back to a pool table and plug in the same, or set up the same situation and hit the ball in exactly the same way, imagining you could possibly do that, you might not get exactly the same result that you got out of your video game version. But it's worth noting that those errors do creep in, and more importantly, that those errors are added energy, and we'll take a look at how we might resolve that. So floating point representation, this is also a case for errors. This is actually the case even with, we talked about being able to accurately find our position. It's not entirely true. If we're on a computer and we plug in this number, we will be off by a small amount, and that small amount will be down to our floating point accuracy. So a floating point number at the lowest level cannot represent an exact line, because it's still binary digits, and it's got a certain number of binary digits that it's allowed to use. And once you get to the bottom of those, it starts to look something like this, right? So our curve, if we had a very precise curve we might follow, we will move up, say, a few binary digits up to represent this, but it's still going to miss it by a little bit. Like there's this small window here. So our space is discretized down to the precision that we accept. It's important to understand too, with floating point numbers, the amount of precision you have, or the amount of tiny precision you have, is dependent on how close you are to zero. So as you move away from zero with floating point representation, then you start to lose digits in your fraction value. So the way a floating point works is that so it's a floating point, a floating decimal point, literally. And that means that as you get larger and larger numbers, it allows the decimal point to sort of move, to sort of represent those larger numbers. So if I want 10,000, I can represent 10,000. But the trade-off is that I can't represent 10,000 plus 0.00001 or something, unreasonably small. I can represent 10,000, and I can represent 10,001 and 10,002. I might even be able to represent 10,002.839, but I can't represent 2,002.8397. It actually fails to represent that 0.8397 and just rounds it to 0.839 or truncates it to 0.839. And so that's really the kind of truncation we're seeing here. But that truncation gets worse if you are representing 10,000. So if I'm representing a number near 1, because again, the floating point representation, I don't need a whole lot of floating point values to the left. I can use a lot more of those points, those digits to the right. And so now, if I'm at 1, I can represent 1.000000001. I can go all the way to the right for quite a bit further than I could if I'm at 10,000. And so what you'll see in physics systems that don't do a good job of this, or don't think about the fact that they're moving away from 0 and representing their floating points at, say, 10,000 or even a million or something worse, is that they're losing precision in their physics system. They are no longer able to represent the very small digits that you're getting. And so this is very, very important to think about when you use physics. You want to keep everything as close to 0 as you can, so that you can get so that you can push off this error as far as possible. So again, it ends up looking a little bit like something like this, because even in a system where we could accurately answer, we're going to be off this line a little bit, right? So it's closed form. So even with this one, we're not stepping through space, right? We're not compounding our error over time. We're just looking at the exact answer, but we're always going to be off the line. But if we add to that the fact that now we're off the line and we're adding this error here, the further away from 0 we are, the faster we add energy to the system. And so the quicker that things blow up. And in many cases, with all the solutions that we'll talk about that allow us to sort of control the unbounded energy, if you get far enough away from 0, the energy gets so large that there's no way to control for it anymore, and so things blow up. And so you'll see all sorts of interesting cases where the physics just blows up simply by pushing things away from 0. Okay, but let's move along from error and go back to collisions. And actually, we'll see other errors here as well. But let's take a look at the ideal collision case. So let's ignore all that we talked about with collisions in detecting the collision. Let's just look at what happens with physical objects that are colliding. All right, so here are two objects. We've got one somewhat larger, maybe a larger mass, and one slightly smaller. They're moving towards each other at some speed, but they're moving exactly toward each other, or almost exactly towards each other. And so what we see is that just prior to impact, we have something like this, right? So we have, technically these two balls or spheres or whatever are hitting each other just barely now, like they just impacted on each other, but they really haven't felt the effects of the force of hitting each other yet. And then when they collide, they will deform to some degree. It depends on what's happening, and there's a lot of sort of internal physics that happen, but we can imagine, at least with, say, rubber balls, we'll definitely get this kind of shape. Even with bowling balls will also bounce and have some kind of restoring force to them, and it works a little bit differently, and it all depends on the internal structure. But let's ignore all that and just kind of understand that it squishes, and then it's going to want to restore itself. And so we have this period of deformation where the balls are continuing to sort of collapse in on themselves and squish in, because again, we're looking at the real world. We have the normal force. We're not allowed to go into each other. We can't actually violate sort of the ghost principle, which says that nobody's a ghost and that you can't actually go into somebody else and take over their body. And so instead, we have to squish. So these two balls squish, and they'll squish to a certain degree depending on how quickly they were moving together. And then by virtue of the fact they're going to unsquish or restore, or the period of restitution, they will move in the opposite direction. And some of that has to do with the material that's being impacted on. Some of it will have to do with some of the energy getting lost to, say, heat and dissipation or sound or other factors. But we measure that as essentially just a coefficient of restitution, which determines how much energy actually gets applied to both. And so there's a total sort of energy that was accumulated in this collision, and then it gets imparted based on essentially the mass of the two objects. So depending on so there's sort of a full force that happens in here, and then the bigger object will actually move away a little bit slower because it's bigger, and so the force doesn't hit as hard, and the smaller object will move away maybe quite a bit faster, right? So sometimes you'll see this where a smaller object hitting a larger object will actually fly away much faster because it actually takes some of the larger object's momentum with it. And that's due to the fact that they sort of got a combined force while they were moving in here, and then some of that was imparted back onto the ball itself, so they sort of evenly split this restored force, this coefficient of restitution. So let's look at that in much more detail. So here's the full math for the restitution force. So we have now two balls that are colliding in slightly different velocities, but the purpose of understanding is the exact point at which they collide. So we saw that briefly in the our FPS shooter, that we were doing a hit with the particle and trying to figure out the exact point at which it hits, and it gives us normal of collision. So in this case, because these two objects are colliding at this point, our collision normal is here. And in some sense, that represents the normal of the surfaces that are being hit. So the normal you can think of as pointing away from the surface. So if I imagine the flat surface at the bottom of our screens here, then the normal points upward. Or if I'm looking at the top of the surface, the normal points downward. It's always pointing the exact perpendicular to the surface. And on a sphere, if you imagine a very tiny space right here, then the perpendicular is going this direction along the normal. Or this one over here is this direction along the normal. And we can kind of, for a given colliding object, we will look at the collision point and the normal respective to that object, but there's kind of two parties participating at all times in any collision, and so we can always think of the opposite party as getting sort of the opposite version of the same thing, but it's really just the opposite, and there's always just a negative sign that ends up being in there, but it's all kind of evened out. So you just kind of flip-flop whatever you're looking at, and then you get sort of the same answer, just with some negative signs in there. So if we look at this, our full restitution force that is coming through involves the mass of both the objects multiplied together, and we get the difference in their velocities, but projected onto the normal. And so this is really just, we can break this out and we can say this is just the velocity in this direction, right? So the velocity here is, so a dot product essentially gives us a projection. So we can look at it and say, if I take the dot product of the normal and the velocity, what I'm really asking about is how much of the velocity goes this way, and ignore any of the stuff that goes this direction, right? Just in 2D. So we ignore everything that's perpendicular to normal. So that's one way to look at the dot product, especially when the normal is a unit length. And so what we get is the amount of velocity that's going this way for V2, and we also get the amount of velocity of V1 that's going this way, right? And we subtract those two to say, as long as they're going, and essentially because we're subtracting them, we actually get a positive number. Because they're going in opposite directions, we're adding those together. So these end up being a fairly large number, really adding V1 minus negative V2, since we're looking in this direction. V2 is going in negative to the normal. So what we really get is the sum of the sort of lengths of V1 and V2 just along this part of it, right? So just along there, and just along there. Notice that I'm looking at the projection. So we've taken the projection along the normal, we multiply that by the combination of their masses, so this is the momentum, and then we turn it into a force. But let's not worry about it too much. And then we have this 1 plus epsilon. So this 1 plus epsilon, epsilon is our coefficient of restitution. So coefficient of restitution is simply a single number that lets us capture all of the weird mechanical factors that are going in there. So if we put a coefficient of restitution at 0, then we get, if you work this out exactly, then what you'll find is the total force here ends up being almost exactly correct, that it negates all of the velocity in this direction and all of the velocity in this direction. And what we end up with is that the balls then perfectly stop at this point. They still have all of the velocity in the perpendicular direction. So they with a velocity of zero, a coefficient of 0 here, what would happen is this ball would then start moving in this direction, and this ball would move. This ball would move fairly quickly in this direction because it would be moving at this speed, right? So it used all of the projection along this direction, and this one would use a small amount in this direction. So this one would move perfectly this way, this one would move perfectly this way relative to each other to the degree that they had velocity going in that way. So absolutely no force would be resulting from their collision other than enough to keep them from interpenetrating each other. Again, the normal force. However, the other version of the restitution of coefficients, or the other end of the spectrum, is a 1, and so that doubles we get a multiplication of 2 here, and what that ends up doing is perfectly adding all of the velocity from this and this back into the full equation, and then they will snap back at opposite speed. Well, if we assume that both the balls are the same mass, then they will get exactly the opposite speed. So they will have imparted upon them exactly negative the velocity that they were going in this direction and negative velocity that this ball was going in this direction. And so they'll move it away from each other at perfectly opposite speed. So a perfect bounce. So again, the perfect inelasticity or perfect non-bounciness is 0, and the perfect bounciness is 1. It's worth remembering that in the world there is neither a perfectly inelastic collision that happens and neither a perfectly elastic collision that happens. And so it's worth where you are toying around with this number, and in the end that's what you're going to end up doing. You will be able to play with this number in the physics system and decide what bounciness you like. Maybe avoid 0 and 1 exactly, rather choose 0.1 and 0.9 as starting points, or even 0.5 in some cases is a good value. It doesn't hurt to look at 0 and 1 and understand them, but they will never look quite right because it will always feel a little bit wrong. If you're not going for accurate physics, a little bit wrong is what video games always feel like. You always land perfectly, and superheroes always land on the ground and don't bounce up at all. Okay, so all of that comes to how the collision works. A lot of this is happening internally for us. The takeaways here are to make sure that you understand both that there's a lot of energy that goes into this, but you can control at least some of that energy into the collision in terms of your elasticity or your coefficient of restitution, which is this little value here that you're adding into this equation. And then thankfully Unreal takes care of the rest for us. It just gives us the velocities on our objects that are doing physics. So one last position of error. We've talked about at least two cases of error, two main cases of error. One is the Euler method, the other is our floating point error accumulation that increases as we move away from 0, recall. And then the last one is this collision problem. So the ideal case is that we're going to collide right here and then deform our objects, but our objects are not deformed unless we add in a lot of extra code to figure out how to do that, and we're not doing that. We're doing what's known as rigid body physics, where we assume that these objects do not deform at all. We still capture some deformation by giving them a restitution force, but the actual physics means that they never change shape. And so what happens is that rather than changing shape, they overlap. And what we do is we look at this as this is the problem that our collision needs to fix. And so in some sense, the way we determine the amount of force, the sort of minimum amount of force that we need to fix, or the amount of momentum that was applied here, has to do with how far into each other they've collided. So the minimum correction, sort of the zero elasticity correction, it pushes these two objects at least far enough so that they are no longer colliding, so that they're back to this just barely touching position. The problem is that if these balls are moving fast enough through space, and recall that we are jumping in time, right? So we've said, based on my delta time, based on my whole Euler update over here, I am going to teleport my position from here to here. I'm not really moving through space here. I'm at this position, and then I'm at this position, and then I'm at this position. And so we are sort of teleporting through space, but very, very small amounts, unless we're moving very, very quickly. So if our velocity is high enough, then we might actually teleport pretty far. And so for a fast-moving ball, or for maybe balls that are very small and also moving very fast relative to their size, It could be that this is like a BB shot out of a gun, and this is, say, an apple or a blueberry that we're trying to hit. So our BB ends up at step T0 here. It's actually probably like T100, and then T101 jumps so far that we are entirely inside the other object. And what we lose is a lot of information about this correction force. Now we still kind of know the momentum. We might say, well, these balls were going this way and this way. We kind of lose the collision point. Just using a collision system, we really don't have edge overlaps at all. And so we don't really know where the proper collision point is. We might say, well, let's just kind of guess one's over here. We might also not be entirely sure where our depth really is and how much we have to push the ball in which direction. Maybe it turns out that it feels like it's less energy just to send the ball back out this way and let them move along their merry way, and that's almost like they never collided. They just sort of magically moved through each other and violated that ghost principle. So in general, this is a problem, and this is a problem that just simply plagues physics systems if you have any object that moves very fast relative to its size. So if it's a very large object, you can probably move it much faster because, of course, if there's a tiny object, in some sense, if the large object is moving really quickly, then it sort of absorbs the tiny object, right? The tiny object might be moving slow, but the large object is moving very fast relative to this. So it all comes down to all of your objects and all their speeds. So in general, avoid very tiny objects or avoid very high speeds relative to those tiny objects. So the ultimate problematic simulation system is actually pinball, and you'll find that 3D pinball games often cheat and use 2D solutions because the 2D solutions are easier, and so they will look 3D, but they will feel very 2D in their actual physics implementation. The ball will not bounce and hit the glass, for instance, or things like that. Another one that, of course, is problematic that almost nobody does, except in our first-person shooter cases, is actually model the real bullets. They will simply treat a bullet as a tiny little thing that moves through space infinitely fast and use a ray to determine whether or not it hits something. So they'll just use a single ray from the firing position and solve it that way. So it's worth understanding this is a problem. This is an unsolvable problem in some sense. So keep that in mind. Small objects that move too quickly is always a problem for the kinds of physics that we're trying to do here. So keep it within the realm of reason. Okay, so the last thing we can do with our collision point here is simulate friction, right? And so the idea behind friction, or at least the friction coefficient, is if you imagine an object on a ramp, then these two objects will stick to each other based on their material properties. So if you imagine something like skis on a ski slope, those objects do not stick to each other. Skis on ice don't have much friction, right? They move very quickly. So we would imagine that in this condition, if this were a human on skis and this were an icy slope, that our friction would be very low. If, on the other hand, this were like a rubber block, like some kind of kid's toy or dog chew toy or something, and it's sitting on a cement slope or, say, a tar road, understand intuitively, that's a very high friction. It's probably not going to slide. And so that's really what the friction coefficient represents. Given two objects, what is the angle at which they're going to slide? And so for very high friction objects, you might actually take a very high angle. You might even go all the way to where it's almost vertical before the object starts sliding down. And for very low friction, you might take just the barest little slope, right? So for the skis on ice, you might just take a tiny little slope and those skis are going to start moving, right? They're not going to be able to get stuck there. So that's kind of the notion of the idea of the friction coefficient. And the way we model that is based on the amount these two are hitting each other. Because every frame I have gravity pulling the block down a certain amount. And so that block is going to be pulled down into this ramp a certain degree, this kind of pulled down. So they're actually going to overlap slightly every single frame. We're going to slightly move down, and then the momentum is going to fix it and push us back apart from each other so that we maintain our ghost principle. We don't fall into each other. But given that, we have a certain amount of information about how hard these two objects are pushing against each other and how much friction then needs to be applied. And so given a certain amount of force downwards and the correction force, the amount of force that's perpendicular is the force that's in the opposite direction of the motion perpendicular to the normal, right? So in the case where our normal is pointing this way, then our friction force is going to be opposite our current velocity in this direction. So our velocity is going to be this way, again, because of all the corrections, and maybe we're not bouncing at all. We've now collided with the surface and we're just doing the correction to push us this way. Our friction will be in some proportion to how much we're pushing against each other. So you get kind of a higher friction the harder you're pushing it. So the higher mass, the higher the gravity, the higher you push in. Okay. So just to reiterate, the friction force moves in the opposite of our velocity. It is proportional to the amount of force going into the normal direction. So it's larger the harder we push down. For most cases, it's going to be related to the amount that gravity is pulling us into the block. But the amount that the actual force is applied is in the opposite direction of the velocity that we're going to go, that we're sliding along to the normal of the surface. Okay, so proportional to the parallel of the normal and in the direction perpendicular to the normal. And it all is based on the coefficient along with how much force is being applied and how much energy is going into the system. Okay, so let's look at friction in maybe the most practical sense, and that is in a rolling ball. And so one of our assignments will include a rolling ball with physics, so it's apropos. So if I imagine that I have this ball rolling in this angular motion. Now recall that when a ball rolls, at least when a ball rolls in the sort of normal way, it is not sliding along the surface. Each of these points, so it's making contact with the surface at this exact point here, and as it rolls, each new point is going to come down, right, and meet the surface, and then touch the surface, and then move on, right? And the same thing is going to meet here and move on. So in that ideal situation where we are not currently sliding, what is happening is I'm actually getting so I've got the friction going the wrong way for this example, but that actually makes sense for the linear motion. So in the rolling case, as I'm moving, my friction, or my sort of force, my velocity in the direction against the surface is in this arrow, right? And so the friction then is going to apply a force this direction. And so what happens is, because my angular motion is pushing me this way, the friction ends up giving us a linear motion this direction. So because my surface, by virtue of the fact that I've got an angular motion, if I allowed slip to occur, I would slip, like my surface would move in this direction relative to our contact point here, and so the friction moves us this way. Gives us a linear velocity in this direction. It gives us a linear force, then that turns into a linear velocity through the whole, force to velocity to position update that we get from our Euler update. Right, so that's the angular motion. The other one is I could apply a linear force here, and by applying a linear force, now I've got a force going in this direction. So it's going to try to move the surface in this direction, right? So the whole ball is trying to move its entire body this way. And what happens is then the force gets applied at exactly this point. The friction force gets applied at this point, and then it applies in exactly the opposite direction and forces us to start rolling this way. Right? So either of these two cases ends up imparting a force. We either impart the force in such a way that ends up being the full linear motion gets applied. So we're trying to apply our linear motion, our angular motion to the thing here, and the friction is fighting our angular motion that way and causing us to then get some linear motion applied. Or we start with some, we're sitting here and we start applying a linear motion from some sort of magical force that's inside the ball that's pushing us forward. Or it could just be literally our, we press the W key and apply a linear force in this direction. And then what happens is the friction then applies at this point and causes it to go this way. Now it's trying to fight the full linear motion, right? But it ends up applying at just this point and causing an angular rotation. So if we had the angular rotation, it applies the other way. And part of that has to do with the two different moments. So we've actually got two inertial moments. One is our angular inertia and one is our linear inertia. And when the friction tries to apply, it's sort of fighting one or the other and ends up applying to the one that's sort of not going to fight it, right? So one of these is 0 and the friction is going to try to apply to one of those two and encounter it. Maybe don't worry about the inertial result underneath. That's what's happening. Understand that it's the friction that actually causes the ball to roll correctly. Or if we wanted to apply a rolling motion and get a linear motion out of it, then we need to have friction. Now we can have a certain amount of sliding, and so that can occur with our ball, especially if we decide to have a very high angular motion. There's no way that the friction can actually keep up. There's a certain amount that the friction is going to just tear down. That and we sort of have two friction possibilities. We have both a static and a dynamic friction available. The static friction and these are two different coefficients that really represent more complicated forces underneath. But the static coefficient is when the two objects are not moving, how much extra force is required or how much extra frictional force is pushing against the velocity. But once they start moving, usually that frictional force becomes less, and so it's considered the dynamic friction at that point. Or at least in some models it's used that way. So we have both a static and a dynamic friction. So in some cases you might run into, once you start sliding, now you're in the dynamic friction range, you'll start sliding even more. But it's worth understanding especially when you're trying to understand a rolling ball's motion or wheels in a tire. Really, it's actually often the angular motion is what's being applied, and that gets converted into a linear motion due to the friction sort of fighting that angular motion. Okay, so let's talk a little bit more about stability. So we've talked many times now about the various ways that errors get accumulated. You can think of it a little bit like this, right? That we have sort of this perfect ideal situation, especially up here where we know our gravity is coming in and we have all this knowledge about that. And in our numerical solution where we're using Eulerian results, we're using delta t's, and we no longer have a perfect t value that we can find anywhere in space. And really what we're doing is adding a little bit of extra error. So our position has both the position and the velocity and this other error piece that accounts for some other magical stuff that's happening. And so it ends up, if we look at it in just this way, it is adding extra positional data to our position. We can think of this error as extra energy imparted in the system by virtue of the fact that it is changing our position. It's adding extra little bits of velocity, which implies that there was some kind of force that came in, that there was some kind of energy that generated that force. Okay, so that's where we get this idea that this is adding energy to the system. And so there's a couple ways that we can resolve that, and we'll take a look at the sort of unreal ways, and then we'll come back to this as we actually go into practice with the physics. One is what's known as the substepping system. So we know now that our delta time is highly variable, right? It could be 100 frames per second in one case, which equates to 0.01 seconds in delta time. It could be 10 frames per second, which is 0.1 seconds in delta time. And so if we're considering our error as being related to how far we're stepping through time, then by shrinking the time, we get better results. And so one of the ways we can do this is to say, well, let's force, regardless of what our frame rate is, let's go ahead and force our delta time in our physics update to be 60 frames, right? And what that means is, let's say I'm running at 30 frames per second, but I want my physics frame to update as though it's 60 frames per second. It means for every normal update, I have to update physics twice, because I'm going to do two small updates for every one normal engine update that's going to happen if I'm running at 30 frames per second. If I'm running at 100 frames per second, physics is fine, because it's going to say, oh, I'm good. I'm going to go ahead and use that 100 frame per second one, because it's not over my max substep. Right? The problem you might expect is, let's imagine that your physics update actually takes a certain amount of time, and of course it does, but it takes enough time that it's actually adding. And so if we run two of those, let's say we're running at 30 frames per second, so our physics update needs to update twice. And that causes us to now, it's taken so long that we're now running at 24 frames per second. So that's okay, we're still running two physics updates, but now we're running closer to 20 frames per second. Now we might actually need to run occasionally with 3 physics updates. And so we were running 2 and 2, but we also had this little extra time that was going in between, and it was causing our physics to need to have a little bit bigger update. So at some point we're going to need a third physics update. So we get that third physics update, and that starts pushing us even closer down. Now we're going to like 15 frames per second. So now we need 4 physics updates. This is what's known as the death spiral. So it's kind of like the more physics updates we need, the longer it takes, even the more physics updates we need, and the longer it's going to take even more. So it's going to continue to decrease our frame rate. So one of the ways that we're solving that here is, well, one way is to make sure that your physics update never takes longer than the delta time that you require for it. So if it takes longer than this delta time, then it's probably going to push you into the spiral of death. As long as your physics update is going pretty quick, meaning that you probably don't have that many physics objects, or you're keeping them all far apart because you're considering your collision spaces, or you're maybe disabling certain objects when they don't need to interact as much, then your physics update will be nice and snappy and you don't have to worry about it. But on the other hand, you can just say, well, I'm never going to allow it to go more than 6. So this is kind of problematic. If you imagine that you're allowing 6 sub-steps when you're doing 60 frames per second, that means that if you're running at around 10 frames per second, that's where you're going to hit this max. So if you're allowing your sort of spiral of death to take you down to 10 frames per second, you might want to reconsider these numbers. So that's certainly something to play with. And then there's another larger piece that we can play with. So we already looked at sort of linear and angular momentums in the nature of the ball, which all comes back over to here. So there's kind of every object has an angular momentum and a linear momentum, and all of those get sort of modified by either collisions that happen or friction that happens at the edges and moves it around. But again, that's sort of the two main sort of forces that apply to the object that move it through space or move it through its rotations. And those are where we accumulate that extra energy, right? So our position through space, or our position in our rotation, the total our error accumulates in those. And so this damping of coefficient here is kind of meant to represent broadly things like the aerodynamics. So a ball falling through the air is going to experience a certain amount of air resistance, or a car driving through space is going to receive some air resistance as it moves through the air. You could also think of a ball rolling through grass is actually going to get some angular dampening due to the fact that it's just the surface is sort of rubbing against the grass, or even more, a ball that's in water is going to be having those water particles rubbing against the surface and causing it to stop rolling. And so that's part of what those numbers are kind of meant to represent. They're sort of capturing all of those interesting complex features that, rather than trying to do real aerodynamics or real water physics imparting on all of these, we just sort of capture a bunch of complicated stuff in a single number again. We've got a coefficient of linear dampening and a coefficient of angular dampening. But the other use case here is that these two always reduce energy. So the way they work is that they take our current velocity and they multiply our current velocity by that dampening coefficient, so 0.1 in this case, and then turn that into a force in the opposite direction of the current velocity. So essentially it just becomes a force, and that force is modified by our mass, so it's not a direct negative to negation of our velocity. But by doing that, it essentially acts as an energy reduction. It actually becomes a negative energy because, again, we talked about the fact that energy is coming in and sort of acting as this other thing, like an energy creates a force and comes in and modifies our position by doing that. So damping is a new energy source that is always in the opposite direction of velocity, but it can act as a way of reducing the energy of the system. Now the practical impact is that if you had a ball rolling on a surface, you would expect it to roll forever, or for a very, very long time, due to the fact that there probably isn't much air resistance. There's probably not a lot of other factors that will stop a ball from rolling. And so by adding high enough linear or angular dampening, that ball might come to a stop much quicker than you would in the normal world. So by increasing our dampening, we actually get a nicer response. It's a better feeling response where the physics feels a little bit softer and squishier, but it's in a way that helps you maintain your energy, right? It helps you keep the errors from accumulating dramatically. So it's a number that you can play with, but it's a number that you should keep in mind as you're starting to see energy accumulation and high speeds happening, things like that. This is the number that can save you by just sort of arbitrarily reducing your energy and keeping your errors from getting out of hand. So we're no longer talking about realistic physics, right? We really weren't, but we're talking about player feel. And so by reducing our overall energy, the player feels the play of the physics better than it feels sort of out of control and out of hand. That as soon as they start trying to roll, things start happening chaotically. Okay, and just to look at that more explicitly, the angular damp, you should think of that as applying only to the rotational energy. And it applies not just to balls, but every object could rotate based on a number of things happening. We already have seen this with cubes rotating through space because they're being shot at by the ball or hitting at an angle, and so that causes them to rotate that way. The angular damp will apply to that rotation as well. And then the linear damp is all about just the straight translational motion that an object has as it moves through space. So as you move from x to x plus 1 or y to y plus 1 without necessarily rotating. And so the linear damp applies only to that. So these are two separate controls on the separate motion, but they do apply to all axes evenly. So there's no way to apply sort of a singular, like a anisotropic dampening in the x-axis versus the y-axis. It's just all linear motion gets applied in the same way. And same with the angular. It doesn't really care about which rotational axis. Any rotation gets damped out. Okay, and finally, so we've talked about a number of issues with the physics and the errors that accumulate. If we were to go back and measure the gravity that Mario is experiencing from the very original Mario game, we find that Mario's gravity is something on the order of 10 to 20 times larger than our gravity. So rather than 9.8 meters per second, he's falling at around 100 meters per second squared, right? And so that is very fast acceleration. He's falling incredibly fast. And the reason that Mario does not have issues is really coming back to the fact that doing collision detection in 2D is easier than doing the collision detection in 3D. So rather than them trying to update Mario and let him fall through space, they actually kind of predict where he's going to fall and find out the exact collision. He also falls and it hits an exact zero. It doesn't bounce really at all, at least in the very original game. And so the physics, in some sense, in very traditional sort of platformers, is highly dynamic and is all about player feel, right? If Mario floated down slowly, or feel like he floated down slowly, if he fell at 9.8 meters per second. And so there are games that do feel that kind of floatiness because they are using maybe more realistic physics. And so it all comes back to what do you want your game to feel like? And what can you get away with the system that you have underlying? If you decide to use 100 meters per second squared, you're now going to run into the kind of problems we were talking about where small objects end up moving very fast relative to their size, and you end up with collision problems due to that. If you specialize your collision system, and you can do that with a 2D game, to do pixel perfect collisions, then maybe you don't care. But if you're using the standard collision system, then you probably can't get away with that level of physics. And so there's some trade-offs. This is why this physics is relatively new and not always used for the full game mechanics. But these are the things that now you can start to think about how you would address with that. It's also worth noting that when you see these floaty platformers, or if you try to make a platformer, it feels floaty and doesn't feel like Mario at all. It's worth maybe going back and actually looking at original footage and measuring it. If you look at Mario over the years, the gravity has lessened. So he started to get a little bit more floaty, but it's worth going and examining these things for those kinds of measurements, because you start to learn things about what makes it feel good versus what might be actually realistic. Okay, and with that, we've reached the end of our discussion on physics and, of course, collision, which we did in a separate piece. As with collision, there's quite a bit more complication that's going on under the hood. Hopefully this is enough to help you feel some level of comfort as you're using the physics engine in Unreal, but there's certainly more to learn, and so to check out the additional information, go seek out some additional information to learn more, especially as you want to understand this even more than what we've discussed here.